In to the next installment of quadratic and function. Right. This time the amount of question is longer, so I'll try my best to finish this within that duration of time. Right. Okay, let's get started. Right. Now, first one. Okay, now in this question we're given two functions. Both are linear, as we can see from here. They all have the format of y equal to mx plus c. All the domain given are all real numbers in this case. So it's a comfort to know that they are all real numbers. At least we know that we live in the real world. These are all real to us. Okay. Now we need to solve this equation, right? So the inverse function of fx is the same as the composite function of gf. All right, now let's get started with this. There are many methods to solve this equation. So here I'm just going to highlight two most commonly used methods. Right? At least those methods that I knew of. Right? Now the first one is here. Okay, let's start off with the first method. The first method is to figure out or to evaluate the inverse function for fx. Now to do that, I will let y equal to 3x plus 2 here. And then all we need to do is to change the subject for this function. Right. So we will have like 3x is equal to y minus 2. X will be y minus 2 over 3. Or if you like, you can also write it down as this. Okay, they represent the same expression in this case. Right. Now, therefore, we can conclude that the inverse functions of fx is given by x over 3 minus 2 over 3. Now there you have it. There's the inverse function for fx. We will need to use this in a while. And then next, I'm going to work with my composite functions before I try to evaluate everything at once. So the composite function okay, in this case we have fx, which is 3x plus 2. And then 3x plus 2 will become the input to the function gx in this case. Right, so here we have, what do we have here? Minus a 4 here. Right. So based on the equations given here, the inverse function is equal to gfx. Now we are going to just substitute our finding from 1 and 2 into this given section. So we have here x over 3 minus 2 over 3 here, which is the same as the composite function of gfx. In this case, we have discovered that it can be evaluated as 12x minus 4 here. Now, my usual take on this is I'm not a fraction person, so I would like to get rid of this fraction 3 here. To do so, I can multiply both sides by 3. So if I multiply both sides by 3, I will have, if you multiply both sides by 3, like this, just to make it clear, because sometimes some of you may not know what I'm talking about. Right now, based on this, we're going to expand your left-hand side expression. So we have x minus 2, which is the same as, in this case, this 6x minus 12. And then from here, we have 35x is equal to, let me see, yeah, it's equal to 10 there. So therefore, we found that x is 2 over 7. Right. Now there you have it. Solving this equation using our knowledge on inverse function. Using our knowledge on inverse function and composite function. Right. Okay, so I hope that is clear. Now next, I'm going to, before I move on, I'm going to erase off all this. Let me show you how to solve this by using the previous identity that I have shown it to you before. Right, now if you are not clear, you can refer to my previous video on quadratic and functions. Right, now here, just to recap, I'm going to use this actually use this identity. So I use this identity of f multiply f composite, or I should say the composite function of f with f inverse will give us an x here. And then we also know that if we produce the composite functions between the inverse of f and itself, that would also yield the same result as x. So we're going to use these two identities here to help us to solve this without using here, without using inverse. So we're going to solve without using inverse. Now, of course, there's a reason why I want to skip the section on inverse. In case you are given a very complex function in this case, but in this case we are quite lucky because we are given a straight line equation, which is quite easy to discover its inverse. Now, in the case where we are given a very complex function, then this method will become very handy, right? Okay, now to do that, I will need to introduce this extra. Okay, now I'm going to write down what is given first as usual. So given is, right, now in order for me to be able to apply this identity, I need to introduce this composite function into the equation given here. Once I introduce it here, I need to introduce it here, left hand side and right hand side. Okay, right. Now this is simply the same as a composite function, so three of this. Right? Now bear in mind the order where you introduce the function f is very important, because it does not follow the commutative law, right? So for those of you who are interested to read more about commutative, you can do so. Right? Okay, now from here, we know that this result is given by this one here. So therefore, I can rewrite this as x. And then here, as usual, now just to recap from the previous section, I have found out my GF. So here I just work out that composite function of GF very quickly. So from here I have 3x plus 2 minus a 12, which yield 12x minus, did I get that right? Minus a 4. So, yeah. Okay. So from here, it just gives us gfx, which is here. I can substitute this as the input to the function of my fx here. So that would yield, in this case, that would be 12x minus 4 plus a 2. So from here, if I try to simplify this, I would end up here, 36x. That will be a negative 10 here. And then I would have myself 35x equal to 10, which end up with the same result as before. So this is the second alternative methods that you can use for those students who like to challenge yourself. And then of course there's a reason why I introduced this. We can use this method if in the case where some of the functions is quite challenging to work with its inverse. Right? So I hope we are clear on question 1. Okay, next I'm going to move on to question 2 now. So don't forget, if there's any mistake in the working, do drop your comment on YouTube, and then I'll try to update any corrections needed here. Okay, second question. Okay, now second one. Second one looks quite similar to the first one. Here we are also given two functions, f and g, but they are no longer both straight line. One of them is straight line, but the other one is quadratic equations. But we are not restricted with the domain itself, so we don't need to worry too much about the domain. Now the first one, solve. Okay, let's use a different color in this case. And now solve the equations where we are given the composite function equal to 11. This will be quite direct to some of the students here because you guys have done this a few hundred times before this. Okay, so I just walk this through one more round. So the composite functions of both the functions onto itself, right? So in this case, I will have f 2x, which is equal to 11 here, and then finally I would have here, which is the input, and then the yield 11 there. Now depending on how you want to manipulate your algebras, both of us would yield the same result here. For me, I personally like to move my negative over the other side. Maybe because I like positive instead of negative. All right. Now in this case we have -6. Okay, -6 there. Since I moved my -3 over, so I have myself a 14 there. And then from here, we're quite lucky in this case. We get a very nice number to work with. Therefore, x is equal to a 5 there. All right. Now that is the first section. Okay. Now second one. Okay, for second one. Okay, so for second one, maybe I'll just write at the side so that while some of you are working on this, you can refer back. The range for gx. So here I'm specifically interested in the function of gx. Okay, so just let me use a different color here so it's easier to differentiate that. Okay. So this is a quadratic equation. Now up to you though. Sometimes maybe as a reminder, just to remind yourself, the domain are all real numbers. Now, whenever we work with quadratic equations, we are quite interested in the stationary point, whether it's minimum, maximum. Here is quite obvious because the coefficient of x squared is greater than 0. Therefore, we expect to produce a convex curve, a smiley face in this case. All right. And then all we need to do is to figure out the vertex. In this case, is the minimum itself. There are many ways to do this. One of the method that you guys have learned would be to complete the square there, right? So I will walk through completing the square one more time in more detail so that everyone can get that. So the whole idea is to introduce this extra term where like term, I would say, that can cancel out each other. Right. Now this like term can be produced using the coefficient of x. So I'm going to take the coefficient for x here, divide by 2. Now don't forget, because it's positive 4, so I'll just use positive 4 here. If it happens, so happen that this is negative, then you have to copy this as negative. So in this case, it's 4 over 2. Right. Now from here, I'm going to combine these three terms together. Now of course, 4 divided by 2, you can simplify that, which is a 2. So if I join these three terms together, that will produce another term that I can put into this bracket here. That is x. All we need to do is have x and then copy whatever number that we have produced here, 4 divided by 2, which is a 2. If you happens to have -4 divided by 2, then that will be a -2. And then the easy part will be from here we have yeah, it should be a -4. There you have it. This is completing the square form, and then from here we recognize that the minimum, the least value of gx is -4. The least value of gx is -4. Now, if you like to look at the graph visually, the graph basically looks something like this in this case. Now let me see here. It looks something like this. The graph should be passing through here, and then we have a -4 here. Right. Now from here it's quite obvious. You don't really need to work out the x-intercept in this case. All you need to do is summarize the range. So the range of gx is where the gx must be greater than or equal to -4. Right? So I'm going to pause here for a while. Continue on with question 3 now. Okay, let's look at 3. Find the set of values of x for which this function gx is greater than 12. Okay, let's see. So let's use this function gx here. So we have 4x greater than 12 in this case. Right. Now at this point, all we need to do is rearrange that so that we can get a general quadratic equation, which is -12 in this case. And then we can factorize this. Okay. Now at this point, now there are many ways to solve this inequality. It's either you memorize the step, or memorize the kind of solutions that we will expect if this function is greater than 0. So I would say by memory or by certain formula, we can write these solutions as x is greater than -6. Sorry, let me correct that. X is less than -6. Okay, by rules, for instance, that you can remember. So x is less than -6, or x could be more than 2. Right? Now, if you want to get an idea where these particular solutions actually came from, right? Now, it's best we are going to draw a graph to represent these quadratic equations, or this one here. It's the same quadratic equations. So if I were to sketch this quadratic graph, so let's see what we have. Yeah. Okay, so we have a -6 here. Then this is a 2. And then this is a convex curve. So we expect that, and then it passed through a -12. I'm not drawing with scale here, so please bear with me. I'm just trying to sketch out what we have here. Okay, for instance, this is the quadratic graph that represent this function here. And then from here, we are seeking to understand which part of the graph that is basically above the x-axis. So we found that this is the sections where the graph is actually above the x-axis, which is somewhere here, this part of the graph. And then it's the same goal for this part of the graph. So we are looking at any x value that is less than -6 would yield this section of the graph. And then any x value that is greater than 2, that will yield these sections of the graph there. Okay, so that's how this result came about. Right? I always encourage you to use visual representations to comprehend algebraic content in this case. It's easier to understand the visual content rather than the abstract algebraic expression here, right? Okay. Now next we're going to move on to number 4. All right, let's see number 4. Find the value of the constant p, for which the equation, the composite function gf is equal to p has 2 equal roots. So let's work out the composite function for gf. So this is given. Gfx is equal to p. Now let me work out the composite function for gf. So we have 2x minus 3 here, which is equal to p. And then finally we have this will become the input to the functions of gx. Okay, there's a bit of algebraic manipulation that you have to do here. So if I do this slowly, I will get 4x squared minus a 6x plus a 9, and then that will be my first expansion. And my second one will be at x 12. It might be easier if you move the p over, because p is a constant anyway. Okay, our intention at this point is to obtain the quadratic expression. Right? So from here we have 2x, and then we have minus 3 minus p here equal to 0. Right. So here we can recognize the coefficient for x squared, which is a, in this case 4. Coefficient for x is 2. And then the constant, it's kind of tricky business at this point when we deal with the constant. For me, I personally like to group this. So when you group it with a bracket, now that will become a plus then. If you expand it, you still end up with the same result. Okay, that's how we check. So once you have written that in the proper format, then we can analyze these sections where it involve 2 equal roots. 2 equal roots, or sometimes just as a reminder, that is a tangent. So once you come across tangent, it will remind you that the discriminant b squared minus 4ac must be equal to 0 there. So just to be clear, I just relabel a, b is equal to 2, c is equal to, now c is equal to negative. If you can treat 3 plus p as a number, so that is basically a negative of that particular number. Now, don't be confused here. 3 plus p could be a negative number though. If this is a negative number, then therefore c will become positive. So it's always good to keep your mind open at this point. Okay, but anyway, this is not our concern. Our concern is just to substitute all this value so that we can find out what is the value for p. Okay, 4a, and then negative 3 plus p here. It's better to use as many brackets as possible for clarification here. Right. So this is 4, 16 here. Because there's a negative here, I might as well expand this negative out to ease my algebraic manipulation here. So I have 3 plus p equal to 0 here. And then you can see that this is basically 52 here plus 16p equal to 0. All right. So here, just let me check. So therefore, in this case, the P, okay, just let me quickly check this. Okay, so that will be a negative 52 over 16 there, right? um, uh, we are going to see whether we can simplify that. Of course, if you use your calculator, then that would actually yield a negative 13 over 4 there. Okay. Now that will be the value for P. Okay. I hope I got that correctly. Just let me check one more time. Right. Now in the exam, this is the situation that you will be facing though. Right now you have done your calculation, you have done your algebra and so on. You are wondering whether you are getting the correct values here. Okay, now just for the sake of checking here, all right, now I'm going to use this value here for the purpose of checking to see whether my works actually is correct, whether this value is actually correct. Okay, so it's a good point to check though, um, if you're not very confident. All right. Okay, how do we check? We are going to substitute this value back into this quadratic equation, and then hopefully that we will end up with one solution. Okay? And then these one solutions indicate that we have two equal roots. Okay, so for checking, I'm going to write it up here. So we have 4x squared plus 2x minus. So if I put this one inside here, then that will be a 3 minus 13 over 4 here, equal to 0, right? And then that would yield 4x squared plus 2x, and then that is basically 1 over 4. Okay, so we can try to simplify that. That is 16x squared plus 8x plus 1 here. And then if you try to factorize this, we have 4x plus a 1 square, which basically yield one solutions here that is equal to negative 1 over 4. I should point out that it should yield two solutions, two real and equal solutions. That's the reason why we can treat this as the same point that we always call as tangent here. So at this point, after checking, I'm very confident that the value that I have obtained is accurate. So bear in mind, in order to make sure all your works is numerically correct, it's always good to check here. Right? So I hope that been helpful to help your mathematics journey, and then how to actually verify your own work. Okay. All right. So let's move on to question 3 now. Okay, I think question 2 there's another section here. Yeah. So just let me scroll up. I think there's another sections under question 2. So just let me. All right, this is the last sections of question 2. Right, is too long to display on one page, so that's why I separate it out. Okay, now for this we have a function. Okay, in this case we are given the function h. Right, now I'm going to write that down. Given hx is pretty much the same as the quadratic equations that we have given. The only thing different is the domain has been restricted here. And it is known that h has an inverse, which means I should make it clear here. inverse exists. Okay, this inverse actually exists. Now, for this to exist, we need to remind ourselves that hx must be a one-to-one function. Must be a one-to-one function. So there's the conditions for the inverse to exist, right? So first step, we can actually sketch this graph very quickly here. So I'm going to sketch that very quickly. I think most of you have seen this graph before. Okay, so let's see. Okay, that's pretty obvious here. The graph looks something like this. Okay, so it passed through the -4, 0, and then you found that the vertex is located at a -2 here, -4. So this part is a -4 here. This is -2. All right. So that's how this graph hx look like. Okay, I need to stress here this graph hx. Sorry, I shouldn't use the hx here. I should say that this graph x squared plus 4x look like where its domain are all real numbers. It's not restricted, and then visually we know that this is a many to one function. Many to one function. So therefore, this function cannot have an inverse. But luckily, for this function hx, they have restrict this domain. They restrict this domain, and then we want to find what is the smallest value of k where we can restrict the domain here so that it is a one-to-one function. So the only way to do that is to make use of the minimum point. So we can sort of split this symmetrical quadratic graph into two sections by using this line here. This line has an equation of x equal to -2 here. And then we know that the smallest value that we can have is x equal to -2 for us to be able to split the graph into two sections. Now it's up to you though, which sections you want to take here. But since they mention smallest possible value and then x is greater than k, therefore in this case k must be greater than -2 for us to be able to have one-to-one function. So by restricting sorry, I think I wrote down wrongly here. Just let me correct that. So therefore, in order for us to get a one-to-one functions for this function here, we must restrict the domain to x greater than or equal to -2 here, which typically will give us this section of the graph. These sections of the graph. Right? And then by doing so, we are indirectly omitting these sections of the graph. We are omitting these sections of the graph. Just let me clean that up. So this is what we are getting after you restrict the domain. So if you restrict the domain in such a way, you can see that these sections of the quadratic graph is a one-to-one function. Now this is 1, 2, 1 function. And then of course at this point I can call this hx now because I no longer use x are all real numbers because we are restricting the domains to anything more than -2. So they are asking what is the smallest possible value of k. Of course the smallest very obvious at this point, smallest possible value of k is, I think you can guess that, must be -2. Right. So that is question number 5 then. Right. Okay, so I hope that is useful. Right. Now next, we're going to work out the inverse function. Since the inverse exists, so we want to work out the inverse functions then. Right. Okay, now I just erase all this. Just let me rewrite this one more time. I'm going to say that smallest value of k is -2. So I'm going to write down the last part here, number 6. Number 6 here. So find the expression. Find the expression for the inverse. Okay. Now I'm going to make use of what is given here, the hx, which is x squared plus 4x. Now in terms of completing the square, we have this. It's always good to check through in this case. Okay. And then by using the traditional methods of finding the inverse, we can let y equal to x plus 2 square here. And then by some algebraic manipulation here, we can get ourselves, I would say, x plus 2 square. I'll do it slowly here, plus 4, and then therefore x is equal to the square root here minus a 2. Now don't forget, whenever, okay, I better show this section here so that it's clearer for some of you. X plus 2 is equal to plus or minus here, right? But anyway, we know that at this point the lowest value for y is actually a -4. The smallest value is -4, right? And then the smallest value for x is -2. Okay, so if you rearrange this, we have x equal to plus or minus y plus 4 minus 2 here. Okay, so you must be wondering, should I be choosing a positive number or should I be choosing a negative number then? So that must be very interesting to ponder on, right? Okay, now if you can't decide, so let's make a small experiment here then, right? Okay, take for instance, let's assume that we're going to choose a negative, for instance. If you can't decide, for instance, okay, let's choose a negative. If you go for negative, and then we know that the y value is more than -4, which means this expression, this square root expression, will be a positive value, and then therefore your x will become more negative, which eventually will be less than -2. And then if that happens, we are out of the domain. We are somewhere here if you are looking at x less than -2. Because before that, we have already restricted our domain to anything more than -2. So if this is a negative, therefore this piece of the functions must be out of the domain in this context. Therefore, this cannot exist in this context. And then because of that, we have to choose the positive version of this function. Okay, so I hope that is clear. All right, now knowing this fact, we can finalize the inverse. So therefore, the inverse function of h must be x plus 4 square root minus a 2. Now, if you want to put more detail into these inverse functions, this inverse function is true for all the x value where its domain is actually greater than or equal to -4. Yeah, because this domain is actually the range for hx is, to be clear, we write down -4 here. Because the range for hx is more than -4, therefore it will become the domain for these inverse functions here. All right. So I hope that is clear. Okay, so just let me clean this up. We are done for this. Okay, maybe I get a bigger eraser. It will take a long time to clear this up. Okay. Right, there you go. That is question 2. Right, now we are going to go to the next question now, question 3. All right, question 3. Okay. So for question 3, we are given fx as 6 minus 4 cos half of x. And then the domain given, or x between 0 and 2 pi. So maybe this is part of a reminder that x value is measured in radian. So put your mind or evaluate all the x value using the radian measure. Okay. Okay, I hope that's clear. And then first one, we need to find the exact value of x for which fx is equal to 4. Right, this is very straightforward. All we need to do is just so follow the instruction. It says that fx is equal to 4, but fx is given by this detailed function here. It's equal to 4. Now, this is a very interesting way of manipulation. Now I'm going to show the way how most of us would actually manipulate this. Okay, now most of the time you would actually show this step, which will yield -2. Right, now we know that -2 and negative here we can remove them, and then 4 and 2 we can also remove them, so therefore we have 0.5 there. Right. Now, no matter how you manipulate your algebra, that is fine. Eventually, we will reach at this section, which is the most important section. And then after that, we can evaluate the solutions for this, which is by taking the arc cos or inverse cosine here. Now, if you press your calculator on this, it will give you 60 degrees. Now, again, a reminder, your angle must be in radian measure. So 60 degree is pi over 3. Right? Now, again, for those who study trigonometry, you know that there is another solution which is possible within that 2 pi radian domain. Then that will be 5 pi over 3. Okay. Now at this point, if you are not very sure which one to choose, or are we supposed to choose both of these solutions, never mind. Okay, we are going to solve them anyway. The more the merrier it is. Okay, then we can decide later on. So the solution for x would be 2 pi over 3, and then the other one is 10 pi over 3. All right. Now here we can conclude that x must be equal to 2 pi over 3 because 10 pi over 3 already exceed 2 pi, which is out of the domain. Therefore, our solutions is this one. Right, so I hope that is clear. Number one. Right, now second one. Okay, let's look at second one. Okay, second one. We need to set the range for fx. Now there are two methods how we can obtain this easily. Okay, I'm going to show you the a more lengthy methods, right? Or maybe it's a traditional way of finding out the range of fx is by using graph. Okay, by using graph. In order to use graph, we must sketch out this particular graph here. Okay, now there are many ways to do this, I would say. So let's try to sketch out a graph. So just let me get the axis here. Okay, just let me get the axis that we need for the graph here. All right. I think we are ready at this point. So I'll label this as fx. This one will be the x. Bear in mind is this in radian measure here. All right. So maybe I will start from like you're going to choose your proper scale though, so that you can sketch exactly how the graph will look like. But extra information on this graph would be this particular trigonometry function has an amplitude of 4. It always fluctuates between 4 and -4. Okay. Now the original graph looks something like this. So I might want to sketch the original graph. The original graph for cosine basically look something like this. Just let me try it out. Okay. So basically, just let me try to sketch this graph out. Okay, I will try to sketch this graph. Let me do that slowly. Hold on, sorry. Hold on, where is my eraser? Okay. Now let me work out the graph slowly here. So I'm going to start by working out these sections of the graph, which is 4 cos half a x. Okay, how would that graph actually look like in this case? So I can start by laying out my scale here. So I know that it should range up to 2 pi. So how am I going to divide them? Right now, that is entirely up to you in this case. So maybe I'll put like a pi here, and then 2 pi here. Right now, in between, if you like to further divide them, you can. So take for instance, this is pi over 2. This one will be 3 pi over 2 here. Right, and then if you want to further divide them, that's entirely up to you, right? So we're going to try to sketch this graph here. Okay, at x equal to 0, so x equal to 0, you have a 4 here. So maybe I'll just put a 4 here. Okay, just let me see whether I got that. Yeah, there's a 4 here. And then after that you have because this graph, okay, I just label y here. It's easier. Okay, so for the graph y equal to 4 cosine half of x, it started off from here. So when x is equal to 0, it passed through a 4, then it will substitute. And then when you substitute pi over 2 into here, you would end up with 2 sub 2. 2 sub 2, which is around 2.82. Which is around 2.82. Okay. So 2.82. Okay, I think this scale is a bit ridiculous. Just let me change it. Okay. 2.82. So maybe this is 2 here, and then this one is 4 here. It's easier for me. So 2.2. So 2.8 something might be somewhere here. Yeah, might be somewhere here. And then you can try out using the pi. So pi is basically a 0 here. And then you can try using 270 degree. Okay, 270 degree, yes, correct. So in this case, if you put that in, that would be a let me see. This is a 90 degrees, so that is negative. So it's actually a negative 2.82. So this is negative 2 here, 2.82. So that should be somewhere here. And then finally, if you try 2 pi, you get a negative. Sorry, 2 pi. Pi is negative, so that is actually a negative 4. So there's another one down here. Okay, sorry, my graph is not very. Just let me extend it. Okay, that is the worst axis. Just let me extend it properly. Okay, so from here, I can put down negative 4 here. So basically, the graph looks something like this. Alright, within this particular domain, for this particular graph. Right? Did I get that right? When it's 0, oh, when 0 is 4. Okay, sorry. I think I drew wrongly this part. Just let me correct that. Okay. So when x is equal to 0, the y is equal to 4. I think I accidentally referred to the previous. So the correct graph would look something like this. Right, now this is the graph for 4 cos half of x. Alright, now I hope you are clear with this here. Alright, and then how am I going to get negative? Yeah, my next intention is I'm going to sketch y equal to negative 4 cos half of x, right? Because there's a negative 4. So in order to do a negative 4, what happens is that it's quite easy to just reflect. All you need to do is reflect this about x-axis. Just reflect this about x-axis. Then therefore, you will get this particular graph here. So just let me reflect that. So basically you have something like this. Just let me put down the appropriate term there, a point, sorry. So therefore I would have something like this. Alright, so that will be this graph, y equal to negative 4 cos half a x. Okay, now I'm almost there. Finally, I need to include the 6, which means I need to translate this 6 unit up. So if I translate negative 4 6 unit up, I would end up with, okay, I would actually end up with somewhere here, for instance. So 6, I would actually end up with a 2 here. And then if I translate this, it would end up with somewhere here, and then this one would be somewhere here, for instance, and then this one will be somewhere here. Then you will see that this would be translated up. Okay, hold on. My drawing is a bit not very good. Just let me make it smoother so that it look more convincing. Now you can see this graph. The green one has been translated 6 units vertically up, and then that will be our final graph. This one here, just let me clean this up. So that is fx equal to 6 minus 4 cos half of x. Right. Now the big question is here. I need to get more detail for this graph. Okay, so just be patient a bit with me. I'm going to scroll this up so that I can have a bit of space to draw this. Okay, so let me extend this section here. So most of the time it's more trial error. Okay, hold on. Just let me clean this up. Just let me extend this further. Okay, that is not very convincing. Hold on, just let me. Oops. Wrong color. Is it correct? Okay, hopefully this time I get it right. Okay. Hope that is okay. It's not very nicely done, but it should be sufficient at this point. Okay, so once we shifted up, once we translated up, now it would actually give us from here, this is 4. So if we translated up, this value here would give us a 10, because a 4 plus a 6 unit up, that would actually give us a 10 there. Right. Now that will be our final graph, 6 minus 4 cos half of x. Now I'm going to make use of this graph to determine the range for fx. Therefore, the range for fx is given by, you can see that the lowest value for y is a 2, and then the highest is 10. Therefore, we can say that the range for fx is actually lying between a 2 and a 10. Right. So if you are not very familiar with graphing methods, it will be a bit challenging at this point. But anyway, if you dare to challenge yourself, it's a good learning curve. Not only you learn how to understand trigonometry ratio cosine better, you can also revisit transformation in this case, which is a crucial mentality in solving some of the very challenging mathematical problems here. Right? So you can use this first method to answer second section, sorry. Right? Okay, next. Of course, for students who are not keen to apply graphical methods here, I'm going to show you a simple and yet easy to use method to obtain the range for fx here. Right, so before that, just let me clean up all this. Alright, just let me scroll back to the question so that we know what we are looking at. Okay, this is our question. Right now we are at second sections here. How do we find the range for fx without drawing? Okay. Without the help of graph. Okay. Now, even though without the help of graph, we need to understand more about these trigonometry functions here. So we're going to make use of our understanding of the range for cosine. You must recognize that any cosine or sine always lie between 1 and -1. Now that is the same for cosine half of x, also lying between 1 and -1 there. So by making use of this understanding, we can we can determine the range easily. Okay, so the maximum range for cosine is 1. Minimum value for cosine is -1 here. Okay, so from here we're going to find the minimum. Let's try to find minimum value of fx. So minimum value of fx is given by 6 minus 4. So we need to check out what is the minimum value for cosine half x. So the minimum value for cosine half of x is actually, okay, based on this, we know that it's actually -1. Okay, you can try that out though. You may think that, okay, since I'm finding minimum value of fx, I might as well put in smallest value for fx here. Okay, let's give it a try, then try our luck. So in this case, we found that it's 10. At this point, we are not very sure though. We can leave it out there. And then after that, we are going to continue on to find the maximum value of fx. And then here it does indicate this is kind of like maximum value for this. So we're going to substitute that maximum value. Let's give it a try. And then in this case, we found that it's 2. Here we state that it is minimum, but somehow the minimum value is larger than the maximum. Yeah, this happened because there is a negative sign there. So to do this properly, the actual way to substitute, sometimes you have to apply a bit of common sense. 2 definitely must be minimum there. So it's best we change this, we interchange this value. Okay, just let me correct that. So in order to get a minimum value, this section here, this value that we are trying to multiply must be maximum. In order to get this value to be minimum, this value found inside bracket must be maximum. So we are supposed to look at the maximum one here. So that will actually yield 2, which is exactly minimum. And then to get the maximum value for this 6 minus 4 multiply this, you want to get the maximum value here. We want to pray very hard that the number inside bracket will be the smallest as possible, right? As small as possible in this case. So the smallest that we can have is actually -1. So from here we get ourselves a 10. Therefore, we can conclude that the range for fx lying between a 2 and a 10. Yeah. Okay. So if you like this, a more direct approach, you can, by all means, you can use it. Right? Okay. So I'm going to clean this up. We're going to move on to the next one. Okay. Next, let me see what we have. All right. Next one, we're going to sketch the graph y equal to fx. Okay, now I have indirectly sketched the graph for y equal to fx just now, so you can refer to the previous sections for this, right? Or maybe I'll just sketch it here very quickly for your reference. So the graph for this is looks something like this. Just let me hold on. Going to use a different color here. All right. Let me set up the axis here. Okay. Just let me summarize it one more time. This is fx. Starting from 0, we know that the lowest value for fx is 2, and then the highest is 10. So I'll put 2 and 10 here, and then we know that the domain is 0 to 2 pi. So just let me put that in. So assuming that this is a pi, and then that will be 2 pi then. All right. So we know that as 0 just now, we get a 2 here. And then we know that at the 2 pi, we got ourselves a 10. So just let me roughly estimate that using a guidelines here. Easier to follow. Okay. And then at the pi there, we have a 6. Okay, so 6, just nice, is actually in between though, somewhere here. There's a 6 there. Okay. So the graph for this would look something like this. Hold on, just let me redraw it one more time. Doesn't look very convincing in this case. Just let me, yeah, okay, that will be much more better. So this will be our graph for fx equal to 6 minus 4 cos half of x. Yeah, of course you can revisit the transformations before you actually end up with this particular graph here. Right? Okay, so I hope that is clear to you how this graph was sketched out. Okay, and then finally we need to get the inverse functions for this. Okay, so just let me erase this, and then I'm going to write the inverse function here. Just let me label this as fx equal to 6 minus 4 cos half x here. Right, now as usual, to get the inverse functions, we will let y equal to, this is number 4 here, let y equal to 6 minus 4 cosine half x. And then with a bit of manipulations here, so we have 4 cos half x equal to 6 minus y, and then you have cos half x, right? So divide by a 4 here if you like, so that is actually 6 minus y divided by 4. Then therefore we have half of x equal to the inverse cosine. Sometimes you like to call it arc. Then x is actually equal to 2 cosine 6 minus y over 4. Hence the inverse function for fx is given by 2 cosine inverse 6 minus x over 4. Alright, and then now it's just my bad habit. Usually I will write down the domain for my inverse. My domain for my inverse must be, the x must be lying between 2 and 10 here. So at least I know that in order for me to have an inverse, it must satisfy the conditions of fx should be a one-to-one function. Right? Okay, so I hope that is clear here. Right, so I'm going to move on to question 4 now. Just let me check one more time if there's any extra section. Okay. Alright, question 4. Okay, question 4. Now the function f is defined by this quadratic equation for all real number x. Find the set of values of p for which the equation has no real roots. Okay, that is pretty similar to all the questions that we have done so far, right? So all you need to do is given here, follow the instruction. Given fx is equal to p. Now that actually means 2x squared is equal to p here. Okay, as usual, we're going to arrange this. Okay, and then having no solution or no real roots or no x-intercept here suggests that discriminant b squared minus 4ac must be less than 0. Now again, as a good practice, I will always write down my A is this, my B is -6, C is 5 minus P here. Right? Now, then only you will start to substitute. So my A is here, my C is 5 minus P here, less than 0 there. Okay, so here we have 36, 8 minus 5 less than 0 there. So from here you get a -4 plus a 8p less than 0. Now p must be less than 0.5 then. Okay, so check one more time just before you finalize. P is less than 0.5. Okay, so that is what we have. So set of values of P. So sets of value of P. P would P are all real numbers, or if you like, you can write down P are all real number such that P is less than 0.5. Okay, so that will be the solutions for number 1 here. Of course, in the exam, if you can reach here, it's considered as the final answer. Right? Okay, I hope that's clear. Right, now next I'm going to clean up the sections here. We are going to move on to the second sections. Right. So second sections is the same quadratic equation, but the domain has been restricted here. Okay, restricted to between 0 and 4 here. Okay, so let's see what do they want. Express gx in this particular form, completing the square form where a, b, c. You must recognize that a, b, c are constant, but other than knowing that they are constants, there's no other restrictions imposed on a, b, c. So we are quite comfortable with this. So let's try to proceed on with the normal procedure on how to produce the completing the square form. Right, now I'm going to rewrite the original function. Okay, and then in this case, the usual way that I did would be I would factorize this. Main purpose is to make sure the coefficient of x squared is a 1. It's easier to work with the completing the square form later on. So from here, I'm going to simplify the work a bit. I think most of you have done that many times already. So that will be 3 over 2 here, square. And then, of course, in this case, you will have a 9 over 4 here, plus a 5. And then by expansion, so we have this, and then that will be like 1 over 4 after you simplify with 5. Okay, just let me roughly check that. 10 or 1. Right now, it's always good to verify whether this is the correct complete the square. So I'm going to mark down here checking. Checking point is super important. So to check, I'm going to expand this to see whether I'm able to obtain the original expression. So 2x squared 3x plus what do we have here? Okay, 9 over 4 plus 1 over 4 here. So I have 2x squared minus 6x plus 9 over 2 plus 1 over 4 there. And then therefore I get 2x squared minus 6x, and then 2, 18, 19, this is 2. Just let me check one more round. Did I get that correct? Okay. Doesn't seem to be correct though. You can see that that is a -2. It's a 10. It's a 1, 4. That is a 9 over 2. And then in this case, if I put a 2 here, 18, 19, 19. That is actually 19 over 4. Now you know. You can see that answer does not tally. Okay, does not tally. So maybe it's time to check what went wrong. Do you see that I also make mistakes sometimes? But I do recognize where is the error. But it's good for you to recognize where is the error than for me to know where is the error. Though. Okay, now let me point it out without wasting your time here. Okay, if you actually slowly work this out, so this is like correction here. Okay, correction. So you can see that if I slow-mo this, it's not really slow though. So this is 9 over 2 plus a 5. And then if I were to proceed on here, I should actually get a 1 over 2 instead of 1 over 4 here. So this is where my mistake is. So this is supposed to be a 1 over 2. So if I put a 1 over 2, okay, so if I change this to be 1 over 2, this one to be 1 over 2, and then this one to be 1 over 2, and then there you have it. Do you see that? I have successfully checked that my answer is actually correct. So once you are happy with this, it doesn't take long for you to check though. So bear in mind. Now therefore, the correct answer for GX, I'm going to write it down here. Bear in mind, don't erase your work. It's a good learning curve in this case. So 2x squared minus 6x plus 5 is the same as 2x minus 3 over 2x plus 1 over 2. Now I'm fully satisfied with my completing the square form. I need to check my A. Okay, the A is there. Is this a constant? And then my B is negative 3 over 2. My C is 1 over 2. Okay, I'm a happy man here, right? So if you're happy, we can finalize the answer here, right? Okay, so just let me put a box there so that you don't stumble onto the wrong answer. So this is the correct answer here. Okay, we are done with number 2. Find the range for GX. So finding the range for GX is not really tough at this point now. You can check the previous questions for this. All we need to do is recognize the vertex or the stationary points here, which we can get that very easily from this completing the square form. So just let me rewrite the completing the square form. GX, which is 2x minus 3 over 2 square plus a half here. So we know that the least value of GX, the least value of GX is a half. And then this occur at x equal to 3 over 2 here. All right. And then therefore, of course, to be more convincing, I might want to sketch out the graph just in case. So the graph is a good way to check whether I have evaluated the range correctly. So from here, there's 1.5, 1 here, and then it should look something like this. All right, so it's somewhere here. Therefore, the range for this function, this particular graph exists for any value that is greater than the least value for this function gx. So now I'm going to conclude that the range of gx is given by gx greater than or equal to a half. Hold on, I think I plot the graph wrongly though. It's a half and an x. Okay, hold on, just let me correct this. How careless I am. But anyway, as long as you recognize the error, that is a new knowledge for us, right? So the graph actually start from here, 3/2 and a half here. So the graph supposed to look something like this. So where this is a 5, this is 3/2 and a 1/2 there. So we know that the lowest point is half. Therefore, we can say that the range of gx is greater than equal to half. Now, of course, don't be too careless or too happy with the answer. Do double check though, even though it looks very similar to the previous questions there. But for these questions, they have these little sections that you must pay attention to. They have actually restricted the domain from 0 here until 4. Until a 4. So let's assume that 4 is somewhere here. So they restricted the domain from here, from this 0 here, until here 4. If they don't restrict this, if they say that the domain are all real number, yes, I could have gotten this 100%. The gx should be greater than half. Okay, but unfortunately, this answer does not satisfy the requirement for this restricted domain. So I need to clarify this, right? So you see that at this point, I'm happy with this result, but I'm not very happy with my domain there. So never mind. Since we recognize the requirement there, just let me clean up. We're going to come back and work this one out again. So just let me clean this out. Okay. Now all we need to do now is to find out what is the y value that I'm not very sure whether this y value is correct or not. So this is just a rough sketch. So at x equal to 4. So I'm trying to find out what will be the value for y then. So I'm going to put this one in there. So that will be like 2 at a 4. So there's a 5, 2 square plus a half there. So in this case, I get 25/2 plus 1/2. That would yield 13. So I know that this is a 13. And now, once I know that this is 13, then I'm going to observe the graph as a whole. I recognize that the lowest value for this graph is within this particular domain here is half. The lowest value is half, but the highest value is 13. Therefore, I can conclude finally the range of gx. Okay, so the range for gx would be, in this case, I know that the lowest point is actually a half. It's still a half though, but the highest point is no longer infinity. The highest point is only up to 13. If I were to touch up this graph so that it fit into this domain, right? Now the graph would look something like this. So let me see whether I can touch it up properly. Just let me clean this up. Okay, there's a 5, and then I'm going to touch up the other sections. Yep. Okay, because this is a inclusion, so I might want to make it clear is including this value, these two values here. Now that is the overall graph within that domain that we have. Okay, so I hope that is clear. Do double check. Do always double check visually, or you can do algebraic checking to ensure that all the result is correct. Okay. All right. Good. Let's move on to the next one now. All right. got the wrong eraser. Okay, just let me get a bigger one here. I think there's another hidden sections from here. Yeah, correct. So just let me um, review that because it's too long in this case. Just let me scroll up. Okay, we're looking at this function hx restricted within this domain. Set the smallest value for k for which h has an inverse. So as usual, this function is nothing different from the previous one. All I need to do is just rewrite one more time the function hx in the completing the square form. Okay, completing the square form. Hopefully I recall it correctly just a moment ago. That would be a half. Okay, just let me roughly check that out. Yes. Okay, a half, a 5. Yep, correct. And then this has been restricted within this domain so that we can have so H inverse exists. That is what we want to achieve. That's the reason why we need to restrict the domain here. K is a constant. So what would be the smallest value for K for which H has an inverse? So same old thing. I'm going to sketch out the graph one more time. Okay, then we can decide from here. Okay, hold on, just let me get the line straight a bit. Okay, we have already seen the graph just now. I just redraw everything out for the domain of all real numbers. Okay, this is for the domain of all real numbers. This is a 5. The same thing here we have, I just pointed out 3 over 2 half, so it's easier here. And then now we know that this is a many to one functions here, which where the inverse cannot exist. How can I make sure the inverse exists? I need to restrict the domain, and then here they want us to restrict it within the domain of x greater than k and then less than 4 here. And then I know that at x equal to 4, that actually yield 13 there. And then this is inclusive. So just let me clean this out. So which means it looks something like this at this point. So how can I restrict by my domain so that I can have one-to-one function? All right. Now it's very obvious visually from here. I should actually cut off the graph. This is hold on, just let me clean that up. The line is not very straight. Okay, so I need to divide this graph into 2 sections. Anything more than 3 over 2 and 4, then this piece of graph would be a 1-to-1. So the best way to do this is to actually restrict the domain. So let me rewrite the algebraic requirement. So the restricted domain to ensure the existence of inverse hx is given below here. So the x must be greater than or equal to 3 over 2, and then must be less than a 4. Right. Now knowing this, if I retouch up the graph just to convince you that it is a 1-to-1, so I'm going to touch that up. So this one does not exist anymore since I restrict these sections of the graph. Okay, so now you can see that this section of the graph is a 1-to-1 function within this given restricted domain here. All right, and then there you have it. That would be the smallest value. Oh yeah, sorry, I haven't answered the question yet. Smallest value. Okay, let me rewrite that. Smallest smallest value, no? Smallest value of k is, all right, now that will be very obvious, is 3 over 2. Yeah, actually I shouldn't have put in equal sign anymore. Is 3 over 2. Right. Now, I hope you're okay with this. Now the last part, for this value of k, find an expressions for the inverse. All right. Now the inverse shouldn't be that tough, so I just rewrite down here so it's easier for you to follow. 5 here. Now, as usual, we will let y equal to its completing the square form, which is easier to work with. So from here we have the x minus, I do a bit of shortcut here. That will be, what do we have here? Y minus 0.5 divided by a 2. Okay, that's what we have. And then that would actually lead to x equal to 3 over 2 plus y minus 0.5 over 2. Did I get that right? Hold on, divide by 2, square root, yes, correct. So there's one thing I need to remember, to square root this. Just let me double check that one more time. Minus by 2, then square root. Yes, correct. Okay, here a reminder again, I'm choosing a plus here because we recognize that all the x value are positive. Right? Therefore, I can conclude that from here, the inverse function h negative here is given by it's given by 3 over 2 plus x minus 0.5 divided by 2 square root. Now, given that the domain will be anything greater than, in this case, anything greater than a half, and then anything less than 13. That's just for your reference, right? Which is not required in this question here. Okay, so I hope that is clear. Right. Let's move on to the next one. We are at question 4, I think. We're going to move on to question 5 now. Okay, question 5. Yes, correct. Question 5. Okay, question 5. Let's see. The function is defined for all x are real numbers. But in this case, we are getting a general quadratic equations where a and b are constant. In the case where a is equal to 6, b is equal to negative 8, we need to find the range for fx. Okay, let's try this out. Number 1, given that fx is equal to x squared plus 6x minus 8, where the domain are all real numbers. Okay, a and b are constant, a and b are given here. We need to find the range for fx. So as usual, I might want to work with completing the square form here. So I'm going to do that very quickly now. Okay, hopefully I got that correct. So just let me check that very quickly mentally. Let me see whether I got it right. Okay, so that looks okay to me. And then from here, least value of fx is, so the least value of fx is negative 17. Therefore, range of fx, range of fx would be anything greater than or equal to negative 17. Right now, that will be this, right? If you like to sketch out the graph, like some of you like to do, which is a good thing for checking, no? So just give it a try. Usually I would sketch this out in case I make any unwanted mistake here. Okay, just let me see here. We have a negative 3 and a negative 18 and a negative 8. Okay, so therefore this graph actually looks something like this. Yeah, the graph looks something like this, and then the minimum point is negative 3, negative 17. Okay, and then it intersects the x-axis at 2 x-intercept. You can verify that by checking its b squared minus 4ac. So just let me check that very quickly. Yes, it is greater than 0. And then the y-intercept is negative 8 here. Right. And then from here we notice that for all x are all real numbers, the lowest point is negative 17. So the range for fx must be greater than negative 17. Okay, so this one is checked. Alright. Okay, now for the second one, right? Now maybe we still have a bit of space there. I'll just write down the second one over here. Okay, second one. In the case of where a is equal to 5, the root of the equation fx equal to 0 are k and negative 2k, where k is a constant. Find the value for b and k here. Alright, now let's give that a try. We have fx equal to x squared. A is a 5, so I might as well put in the 5 there. B is the one that we need to explore later, so that is the B. Knowing that these two are the roots or the solutions to these quadratic equations, so we can substitute that into the function. The usual way we are supposed to do would be, okay, we're going to substitute this. We know that fk must satisfy these equations here. So fk is actually k squared plus 5k plus b, right? And then this must be equal to 0 because it is given that fx is actually equal to 0 there, right? Now that will be our first equation, and then we also notice that the second negative 2k is also a solution or another root. So therefore we can actually substitute this in here also. That would yield 4k squared minus a 10k plus a b equal to 0. Now that will be our second equation, right? Now there are many ways to solve this. For me, I would rather take, for instance, you can take using elimination method. So number 1, subtract off with number 2, we have negative 3k squared, and then plus a 15k equal to a 0. Or you can simplify that as k squared minus 5k equal to 0. K is equal to 0 or 5 here. So there are two values for k in this case. And then we're going to check our b now. For k equal to 0, for k equal to 0, b is equal to 0. That is obtained from this first equation here. And then for k equal to 5, for k equal to 5, for instance, okay, for k equal to 5, we have what we have here is 5 squared plus 5 times 5 here, and then plus a b equal to 0. Therefore, b is equal to negative 50. So just double check the result one more time. Find the values of B and K there. Find B and K there. All right. Okay. So that is what we have in this case. Okay. Of course, you can always check whether the answer fit in here by going through the checking process. So that part I'll leave it to you. All right. Okay. I hope that is clear. I'm going to clean this up. Uh, we are going to move on to number 3 here. Okay. Section 3. Okay. All right. Leave the graph there so that we can see why I leave the graph there. There is a purpose for this. Okay. Number 3. Show that if the equation is equal to a has no real roots, then a squared less than 4 multiply bracket b minus a then. Okay. Now, it's up to you how you want to actually do it. Okay. Now, the usual way is by using algebra. So all you need to do is just obtain this function here. This function basically is a translation. This is a translations um, in the horizontal direction. So we can either translate it to the left horizontally or translate it to the right horizontally. Okay, translate horizontally and so on. All right. Okay, let's see how are we going to use this. So f xa equal to a. It says it has no real roots. We'll see in a while. So from here, that is actually xa square plus a xa plus a b is equal to a. Now, as usual, you can expand this. Okay, so we can expand this. Let's try this out. X squared plus 2ax plus a squared plus ax here plus a squared plus b minus a, and then that is actually equal to 0. And just to arrange it so that we can get a quadratic form here. There we have it. Here we have 3ax, then plus 2a squared minus a plus a b. Right. Now, because this particular equation does not have a real roots, therefore b squared, the discriminant, okay, so therefore the discriminant b squared minus 4ac must be less than 0. Right. Now, try not to confuse yourself. This part is a b, this is a a, this is a c. So by using this, we have 3a squared minus 4, this is a 1 here, 1, a c, 2a squared minus a a plus a b must be less than 0. Alright, now let's work with the algebra here. We have 9a squared, 8a squared plus 4a minus 4b less than 0. So right here we have a squared plus 4a minus b like this less than 0. Right, now you can see the obvious at this point. So a squared must be less than 4b minus a. So you can see that here is a minus b, but when you switch to the right hand side, it becomes b minus a. And then we have indirectly proven this. Okay. Now, the reason why I leave a graph here, just to show you that now when we are dealing with this, when we are dealing with fx plus a, just a bit of revisions. Basically, it means horizontal translation. If a if a is a negative number, right? Let's assume that a is negative number. If a is less than 0. If a is less than 0 is a horizontal translation to the right. So you are looking at this graph is basically shifting to the right if a is less than 0. And then equal to a here basically means we have another straight line a, for instance, straight line a, it could be here, for instance. This is y equal to a. If your a is here, therefore you will expect to have two intersections between the straight line y equal to a and the quadratic equations, or the quadratic graph in this case. Therefore, there are two real roots, two real intersections, two real roots. Okay, so where can a be? As I said, a is less than a. Sorry, a is less than a. What am I talking about? Right. If a is less than 0, a would not be up here. So the correct a would be, just let me clean that up. The correct a would be below that. Okay, just let me move that easily so that I don't need to erase it. Looks a bit tidy up. Okay, so if a is less than, so most probably the a will be somewhere here. So this is the conditions where this line y equal to a does not intersect with the quadratic graph. Therefore, it will produce no real roots. No real roots means they don't meet, they don't intersect with each other. So this is the only way we can achieve these types of solutions. This part here is just extra analysis for those students who are interested to know more beyond that algebra context. Okay, so I hope that is useful to you. All right, now next, I'm going to clean this up. Okay, hold on. Just let me check if there's any hidden sections for question 5. I can't remember correctly. Okay, no. So we are done with question 5 now. Let's move on to 6. Okay, 6. Okay, I'll overshoot over there. Right, question 6 is quite short. Okay, we can finish this very quickly. So you are given both functions. In this case, one is a straight line equation, linear function, linear functions, first order linear function, I would say. And this is a rational function. It's stated that the domain are all real numbers except when x is equal to 1.5. Right. Now, because this function failed to exist in this region here, we're going to solve this. Okay, this one look much more easier than any one of the question that we solved before this. So let's get started. Given f, composite functions of f with itself is equal to this one here. So f2 is 10 minus 3 to here, which is actually a 4. And then G4 we can substitute this one here. Therefore, I'm going to rewrite this. So G4, I'm going to write down here. G4 will be 10, 3 minus 2, 4 here. Now, that is actually a negative 5, so that is negative 2. Just let me check roughly. 8, negative 5, negative 5, negative 2. Yes, correct. So the composite function of f with itself would yield a value of negative 2 then. Alright, so f and f. So f and f, that would be a 10 minus 3, 10 minus 3x is equal to negative 2. So here we are basically just trying to solve these equations here. So we have 10 minus 30 plus a 9x here equal to negative 2. Okay, up to you how you want to do this. This is like 20, 18. So that will be 9x equal to 18. Your x must be equal to 2 here. All right. Okay, and then there you have it. Of course, there's a way to check, but you have to check one by one here. So the checking part, I leave it to you, right? Okay, I hope that is you guys are good with this. Okay, let's move on to 7 now. Okay, 7. Just let me move this a bit. All right, 7. Okay, question 7. The function is defined as yet another quadratic equations, but this time we are expecting to have a concave curve. Find the set of values for x for which this particular function is less than -3 in this case. Okay. Yep, we can try to. There are many ways to answer this. Okay, so I'll show you the usual way that most of us will attempt this based on your knowledge in this case. So given fx is less than 3, so fx is 6x minus x squared minus 5 less than 3. So from here you have 6x minus x squared minus 8. Now I'm not a negative fan here, so I would like to change it to positive. So one way to do it, you can move the negative expression to the right hand side. Okay, so therefore I have this. The moment you move, shift it to the right hand side, the inequality is basically more than 0 there. And then factorizations shouldn't be a problem here. All right. Now, by using rules, okay, by using some sorts of rules that we have applied before, we can conclude that x is actually less than a 2, or x is more than a 4 there. And then that will be our sets of solutions for this. Right. Now, I hope that is clear. If you want to check, yes, by all means, we can sketch out the graph for this. Just let me sketch that out. So the graph is here. It passed through the graph for this. We're talking about this graph here. So it passed through a 2 and a 4 here. Now we are going to draw this graph, something like this. Yeah. And then the questions that we are asking, which part of the graph that is above the x-axis. So we found that the part of the graph that is above the x-axis is these sections here, which refer to any x that is less than a 2. And then these sections of the graph where the x is more than a 4. So that would actually yield the solutions to this inequality. Right. So I hope that is clear. Right. Okay. Now, the second way to look at this solution is through graphical representation. Okay, this is just extra information I would like to introduce for some of you who like to know more. Right now, one way we can do it is by sketch out this graph. Okay, now I'm going to sketch this out. Before that, I'll rewrite these functions another time. So that is typically, let me see, it's a 6x minus x squared minus a 5 here, right? So just let me see whether I can sort of factorize this correctly. Okay, so just let me give that a try. That is just let me see whether I got that correctly. Okay, I think I do it this way is easier for me to get the factor easily. So that is -5. So that is x5 x1. So okay, so it does pass through the x-intercept at 1 and 5 there. So now I'm ready to sketch the graph, the original graph here. So from here, I notice that it passed through a 1 and a 5. So a 1 and a 5. Okay, so this is the graph. And then the y-intercept. The y-intercept is at the -5 here. So -5. So the graph would look something like this, of course. So don't forget, this is a concave graph because the coefficient of x squared is less than 0 there. So the maximum point will be located somewhere here, right? And then where does this tree actually come in? From this through these methods here. So the tree basically means you have to draw a straight line. Okay, we are going to draw a straight line, y equal to a 3 there. So y equal to 3. So here I'm going to write down that as y. Oops. Hold on. Okay, so that is a y equal to a 3. Okay, y equal to a 3 here. So just let me get everything clear in this case with more detail. That is a 6, that's a 3, so I believe the vertex is located at x equal to 3 there. So just let me get the vertex, the y coordinate for the vertex. So that is 9 is a 4, so this part is a 4. This part is a 3. Yep, okay. Now we are good to go. Now from here, we notice that there are two intersections. There are two intersections. We are looking at which region where this straight line, y equal to 3, is way above the graph. So we can see that this y equal to 3 is way above the graph for any of this. Just let me partition that out. For any of x that is that is greater than a 4. If you find this intersection here, it will yield a 4. And then there's another intersection here which we have already found, which is 2. So we are looking at any sections where this line y equal to 3 is actually above the blue curve there. Yes, we found that this is actually x less than 2. So this is the second method that you can use to find the solutions to number 1. Or you can apply algebra first, then with the help of graph, you can verify your solutions. Or you can use this graphical method. Okay, so I hope that is useful to you. Okay, I'm going to erase off that. And then let's look at the given that y equal to mx plus c is a tangent to the graph. So show that it satisfies this equation here. First of all, because they are tangent, which means these two, the straight line and the curve is touching at one point. To do this, we will let number 2, let mx plus c is equal to 6x minus x squared, because they are meeting each other at one point. Okay, so that's why we assign both of the y together. Okay, and then by a bit of rearrangement, we have here m minus 6. Okay, just let me clean up some of the unnecessary display there. Okay, and then after that we have 5 plus a c equals 0. Because it is tangent, therefore discriminant b squared minus 4ac must be equal to 0. Again, a is a 1, just for verification, B is, oh yeah, I forgot to put my X. So B is n minus 6, C is 5 plus C, or C plus 5. It is, okay, in this case, is commutative, right? Okay. From here, we can write down m minus 6 square minus 4a, which is 1. The C is 5 plus C. Okay, maybe there's a bit of confusion between the letter that we are using, right? Okay, just try to be clear with this, right? Okay, so from here, we need to check what we need to achieve here. We need to achieve this. Okay, so all we need to do is just expand this, so m squared, 12m plus 36 there, minus 20 minus 4c is equal to 0. Okay, so we have m squared minus 12m, which is here. And then after that plus 16. Okay, we can see that this is actually plus 16. And then this 4c we can bring it to the other side. So if we bring it to the other side, that will be 4c. So now we know that 4c is actually equal to m squared minus 12m plus 16. So have been proven. Right. So I hope that is clear. Okay.